You type a single command, you ask to fix a bug, and perfect code appears on your screen. The assistant seemingly navigates your files, finds the exact error, writes the patch, and runs the tests, all with zero friction. But beneath the surface of that simple text box, there is a massive, high-speed routing and execution infrastructure. The most common error in AI development today is assuming the large language model is the entire product. It is only a component. An LLM is a raw reasoning engine. To build a production-grade coding assistant, you have to engineer the vehicle around it, a system that retrieves exact context, limits operational risk, and verifies its own outputs. If we map this out like a senior-level system design interview, we have to start from a blank slate and define the core requirements. Functionally, the tool needs to answer code-based questions, search files, and generate functional patches. Those features are easy to build in a prototype. The non-functional requirements are what separate enterprise tools from weekend projects. A reliable deployment demands low latency, tight control over token costs, isolated execution environments, and immutable tracking of every automated decision. The absence of these strict parameters leaves you with an unpredictable and expensive autocomplete tool that fails to meet professional engineering standards. You cannot send a multi-million-line enterprise repository into an LLM's context window every time a user presses enter. The system has to process the codebase asynchronously, preparing the data well before the user ever types a prompt. This flowchart illustrates the ingestion pipeline. Raw source code flows in, splitting down two paths. The first stream converts code into dense vector arrays, generating text embeddings for semantic searches. The second stream builds an abstract syntax tree, extracting exact function symbols and dependencies to map the software's architecture. These distinct models merge with metadata, like file paths, forming a unified, searchable index. Standard text documents rely almost entirely on simple vector databases. Code requires mapping exact definitions and structural logic. High-quality code generation begins with an indexing architecture capable of understanding how software components actually interact. Once the code is indexed, the system waits. The moment a bug fix prompt is submitted, the retrieval phase initiates. Large language models have finite attention. When the prompt is flooded with irrelevant files, the model struggles to distinguish signal from noise, directly leading to flawed reasoning and hallucinations. This diagram shows the initial retrieval sweep. The index returns dozens of raw, unranked file candidates. Using a hybrid approach, simultaneous queries look for both semantic intent and exact keyword matches. A ranking matrix then scores these candidates, applying weights based on temporal recency, open IDE tabs, and symbol distance. Finally, the engine curates the massive codebase down to the 3 most statistically relevant snippets. A poor system stuffs everything it finds into the prompt. A production system strictly curates. Intelligent retrieval dictates AI capability. The exact same model will fail with poor context and succeed when handed the right evidence. With the specific code snippets isolated, the system transitions to preparing the final instruction payload for the model. This payload requires a strict schema. The context builder defines the task, injects the retrieved code, establishes constraints, and dictates the exact output format. Next comes the tool execution layer. Because an LLM operates probabilistically, it can never possess unrestricted administrative access to a host machine. We allow the model to request low-risk capabilities. It can read files and search the local repository freely. Actions carrying high operational risk, like arbitrary network calls or file deletions, are strictly gated or blocked by default. When the model does need to alter the codebase, the system relies on a dedicated patch manager. Rewriting entire files often destroys formatting and removes unrelated comments. The patch manager forces the model to generate precise, minimal diffs that only target the requested logic. The LLM must never act as its own security boundary. The surrounding architecture enforces the laws of execution. Generating a valid code patch is only half the battle. Executing that new code introduces severe operational risk. In classical system design, engineers control failure by managing the blast radius. We apply that same principle to unpredictable AI outputs. This architectural diagram shows a disposable sandbox. It provides absolute isolation from the user's host machine. The sandbox operates under strict limitations: restricted file system access, hard timeout triggers, and the complete redaction of environment secrets. Within this secure environment, the system initiates an agentic feedback loop by automatically running unit tests against the generated patch. If a test fails in the sandbox, the resulting error trace routes back to the LLM, waiting for a revised patch to verify again. To prevent the model from getting stuck in a loop of failures, the architecture imposes hard-coded retry limits and token cost budgets. This isolated verification cycle allows the system to independently resolve syntax errors and logic flaws before the code ever reaches a human reviewer. In a live deployment, the assistant will eventually make a bad edit. When that happens, engineers need an immediate way to debug the failure. Here we see the observability subsystem. It tracks every single action, retrieval, and internal decision made during a session. It logs specific telemetry, the exact file paths retrieved, the tools called, the token usage per prompt, the latency, and the resulting diff. To maintain speed at scale, engineers apply aggressive optimizations. They cache repetitive file summaries and route simpler classification tasks to cheaper models, reserving the primary LLM for complex logic. Enterprise trust in AI requires immutable, granular traceability. This diagram illustrates the completed end-to-end architecture. The user query enters the gateway, routes through indexing and retrieval, structures the context, hits the LLM, executes safely in the sandbox, and logs the outcome. We started with the illusion of a simple chat interface and expanded it into a highly distributed, multi-layered retrieval and safety network. Through all of this, generating the raw code was actually the easiest step in the pipeline. The true engineering challenge is bounding an unpredictable statistical model within a predictable, deterministic safety architecture. Mastering these assistants requires shifting the focus toward deterministic system design rather than better prompt engineering.